We present an overview of our method DoGFlow, self-supervised LiDAR scene flow via cross-modal Doppler guidance.
Scene flow provides an important prior for downstream perception tasks like object detection, tracking, and long-term motion estimation. Current methods face two main challenges. First is LiDAR sparsity. Sparse LiDAR signal between time sequential scans makes geometric matching tricky and can lead to incorrect scene flow estimation, as shown in this animation. The second challenge is adverse weather, such as rain, fog, and snow. During these scenarios, the LiDAR scan gets diffused and scattered, leading to lots of noisy points around object of interest, as shown in this figure. In such cases, the geometric information around the object gets removed, making geometric matching and scene flow estimation impossible. In order to overcome the above two challenges, we propose Doppler-guided label transfer. Consider a car which is sensed in addition to a LiDAR sensor by a radar sensor as well. The radar sensor provides Doppler signals, which can be used to put a constraint on the actual object velocity. These constraints are posed as a system of linear equations, which can be used to solve for the object velocity. Once we have the object velocity, we can propagate this label to the LiDAR sensor data, getting dense scene flow estimation. The first step in this process is clustering on dynamic radar points. Each dynamic radar point is either connected or disconnected to every other radar point, depending on proximity in spatial as well as Doppler domain. Once the clusters are obtained, the velocity is estimated for each radar cluster. As an example, we show three vehicles adjoining to each other. The bigger circles indicate radar points colored according to their cluster IDs. This figure shows the resulting velocity estimation. As you can see, the vehicle on the leftmost side has a larger velocity of 26 meters per second, whereas the vehicle in the middle has a slightly lower velocity. Now our method is able to disambiguate the velocities of different clusters. Lastly, the vehicle on the rightmost has a lowest velocity of 18 meters per second. In parallel, we also conduct clustering in LiDAR space in order to remove the noisy points encountered in adverse weather. We first start by performing intensity thresholding to get strong LiDAR returns from the object. This removes most of the noisy points, but also removes quite a few points from the object itself. We first recover some points in the object by associating it with the nearest radar point. Then we perform HDB scan clustering to obtain the object cluster hypothesis. To further recover more points on the object, we associate the low intensity points to the nearest cluster points. And this leads to our final cluster. With invariably, this will have few noisy points, but in this process, we are able to get rid of most of the noisy points. Lastly, we propagate the velocity from the radar cluster to the LiDAR cluster, obtaining the dense scene flow estimation. However, it could happen that one LiDAR cluster has more than one associated radar cluster. In order to disambiguate, we propagate the LiDAR cluster by the hypothesis of the different radar velocity, cluster velocities one by one, and then make a comparison to the point scan in time step t+1. In this case, when you propagate the LiDAR cluster with the red points, we see that it doesn't match with the cluster in time step t+1. However, the blue cluster velocity matches quite well. Hence, we chose the blue cluster's velocity as our dense scene flow estimation. Thank you for your attention.
Here we show a single frame panning from minus 200 meter to 200 meters from the ego vehicle, which can be identified by the colored arrows. The scene flow prediction by DoGFlow matches closely with the ground truth, especially at long range, while also performing good at close range. Here we compare DoGFlow and other state-of-the-art methods with ground truth on a clear weather log. The red and blue horizontal lines visually indicate perception ranges of 100 and 200 meters. The ground truth is available every fifth frame. Now we shift forward and have a deeper look towards the vehicles in a further range area. Methods relying on geometric matching suffer due to sparse LiDAR signals, whereas DoGFlow, independent of LiDAR sparsity, only depends on Doppler signals from 4D radar. Hence, it is more consistent in scene flow predictions at long range. Now we show an adverse weather log where heavy snow removes all geometric information at close range. The Doppler-guided labels coupled with our noise-resistant LiDAR clustering maintains performance for the overtaking truck while minimizing false predictions. On the other hand, ICP flow and fast NSFP are quite noisy in this region. Lastly, we show a rainy weather scenario. Both ICP flow and fast NSF produce noisy predictions in the spray of water produced by the overtaking vehicle on the left. On the other hand, Our method produces robust predictions in this region thanks to Doppler guided label transfer. As a limitation, DoGFlow produces noisy predictions in regions with Doppler blind spots or multipath effects, which can be observed here for vehicles on the left of ego vehicle.